circuit, the two-port network has the impedance matrix Z equal to 40, 60, 60 and 120. The value of ZL for which maximum power is transferred to the load is dash ohm. For a detailed lecture on two-port parameters, please refer to the NPTEL video, Lecture 4, Two-Port Parameters, Short Circuit and Open Circuit by Professor T.K. Basu, Department of Electrical Engineering, IIT Kharagpur. In order to solve this problem, we need to know the concept of Thevenin's theorem, maximum power transfer theorem, and then the Z parameter equations. A two-port network is a network that has two inputs and two outputs. The first port has the current I1 that is incoming, and the second port has the current I2 that is incoming into that port. The voltage across the terminals of the first port will be V1 and the voltage across the terminals of the second port will be V2. Connecting these two ports, we have a set of impedance parameter equations, which is V1 equal to Z11I1 plus Z12I2. Here, Z11 and Z12 are the impedances. Z11 is the input impedance of the two-port network. Z12 is the transfer impedance of the two-port network. The voltage V2 of the second port will be Z21I1 plus Z22I2. Here Z22 and Z21 are the impedances. Z21 is the transfer impedance and Z22 is the output impedance. A detailed video on the derivation of these equations is explained by Professor T.K. Basu in the NPTEL video that is referenced in the previous slide. The Thevenin's theorem states that any linear circuit containing several voltages and resistances can be replaced by just one single voltage source in series with a single resistance connected across the load. This resistance is called as the Thevenin equivalent resistance and the equivalent voltage source is called as the Thevenin's voltage. For maximum power to be transferred to the load, the source's impedance must be same as the load's impedance. Only then maximum power will be transferred to the load. Therefore, when we adjust the load impedance to the value of the Thevenin equivalent impedance, we will be able to transfer maximum power to the load. We are going to make use of these concepts to solve this problem. In this problem, we have the Z parameter equation of this network and we need to find out the value of ZL for which maximum power is transferred. By maximum power transfer theorem, when the load's impedance is equal to the complex conjugate of the source's impedance, maximum power will be transferred to the load. In this network, if we observe, we have a purely resistive DC network. Hence, there is no scope of impedance that is there in the network. If we are connecting an impedance at the load, then according to maximum power transfer theorem, the resistance of this load must be same as the Thevenin's equivalent resistance of the source network. This is the two-port network that is given to us. When this ZL is equal to the Thevenin impedance of this network, maximum power will be transferred to it. The Z parameter equations for this network are V1 is equal to 40I1 plus 60I2. Then V2 is equal to 60I1 plus 120I2. In order to find out the Thevenin's equivalent resistance, we need to be open circuiting the load and looking at this two-port network from the perspective of the load. So, for that, we are open circuiting this and then looking at the network from this perspective. So, in that case, ZTH will be V2 divided by I2, because the resistance is voltage divided by the current. The voltage at the second port is V2 and the current that is traveling into the second port is I2. Therefore, the Thevenin equivalent resistance will be V2 divided by I2. If we find out V2 by I2, we can say that when the load resistance is equal to V2 by I2, maximum power will be transferred to it. In order to find this, we need to make use of the second equation. In order to find out the Thevenin's equivalent circuit, we need to be short circuiting the voltage sources and then open circuiting the current sources. Then we need to look at the network from the perspective of the load to find out the Thevenin equivalent resistance. Okay, so coming back to our aim, we need to find out V2 by I2. So for that, we can divide the second equation by I2. Let me mark this as equation 1 and equation 2. Implies that V2 by I2 will be 60 into I1 by I2 plus 120. We do not know the values of I1 and I2. So let us park this aside and then find out the value of I1 in terms of I2 or vice versa. Since we have short circuited the first port, V1 will become minus 10 into I1 according to Ohm's law. We can substitute this in equation 1, which is this. Minus 10 I1 will be 40 I1 plus 60 I2. Now we have this equation purely in terms of I1 and I2. So this implies that minus 50 I1 is 60 I2. So this implies that I1 divided by I2 will be minus of 60 divided by 50, which is minus 6 by 5. Now we have found out I1 by I2. We can substitute this right here to find out V2 by I2. Minus 6 divided by 5 plus 120. This will be minus 72 plus 120, which is 48 ohm. So V2 by I2 or the impedance looking at the second port is equal to 48 ohm. Hence, when the load impedance is equal to the Thevenin equivalent impedance of the source, we will be getting maximum power transferred to the load. Therefore, when RL is 48 ohm, maximum power will be transferred to it. Hence, the answer is 48 ohm for maximum power transfer.